been a while since I've uploaded something. It's just been so intense. What I've done, I bought myself a Linux computer. I needed it because I was going to install a ROS system. So I've worked with this Linux now for 5 weeks, 7 days a week, 6 hours a day, building a ROS stack. And what the ROS stack is for, I've made it so that it becomes my system that all my robots in the future and those that I've previously built will be able to use the same language and communications. It's got all the correct protocol that I wanted built in, and it's very cool. So I now have ROS working on this. Just one thing about Linux, I love it. I didn't know whether I would, but I love it. The only problem is, it's a bit annoying, is that the Arduino IDE, you have to use a really ancient one because nobody's bothered to provide a better one. But apart from that, it's really, really good. And this laptop is much better. It's a gaming type, a Legion, much faster. My old Microsoft one was crashing all the time. It just couldn't keep up with the amount of data and software being put through it. Now I can load multi-missions. I could put 100 missions on there, and each mission is a section of, I want you to drive from here to here, stop, and then that's one step. And then you do these multi-steps, so I could have multi-steps up there, and then the protocol boots in and it makes sure that there's no mixed messages. It won't allow it. It's very, very cool, this ROS stack is. It's the hardest thing I've ever done, I must admit. This section here I'm saving for when I build sonar. I'll build my own sonar, and that will be giving me a almost live display of the lake bed. It won't be instantaneous, there'll be a slight latency.
So you've talked about a lake bed, but you've not talked about what you actually do in here.
This is it's a submersible. It's going to be autonomous, and it relays all the information. So first we'll be able to send it on a surface mission, and eventually it will get the sonar depth and profile. Then I can send a dive command, and it will go down for the duration I time it and the depth I time it, and have a closer look. Then it will surface and it will relay back all that information through to here. Now the ballast system that I've gone for is a pony cylinder in there. That's capable of 4,500 psi, but a working pressure of 4,000 I'll use. At the moment, I've got 1,000 psi of nitrogen in there because it's just handy for me. And it's been in there for over a week. I'm just checking that my valve switches on and off and seals properly. So far it has. I'll show you what that's like. It's very cool. Also, I've built this servo tester. This is my servo tester. It took about an hour and a half to build. And I built it because those cheap Chinese ones you buy for about $3, they're a nightmare. When you've got a lot of servos to test, they're erratic, they're very annoying. So I built my own, and I can program it to do what I want it to do. And I should have done it ages ago. So I'll just show you the pony cylinder working. So this pumps out at, well, up to 4,000 psi. And that will go into a regulator, a scuba first stage regulator, which is this. And that takes the 4,000 psi and delivers 120 psi, which is variable. The deeper you go, the higher that will go up, but not too much higher. And that will deliver air pressure through these ballast units. I'll come back to that. First, I'll just show you where all the air pressure will be stored. So at the moment we're at 1,000 psi. When it gets a command to release and come back to the surface, it will open this up like this. You see that moving? And that will put the required air into the ballast system, and it will deliver that through these systems on the bench there. So we have a pair for each tank. That's a tank, and they fit in the ends. And that high pressure air you saw will come in through here, and these will be at the top of the tanks, and they'll fill with air, and at the same time these valves will open and allow the water to be pushed out. And then when it's empty, it will seal those up so no water gets in. And it will all be controlled with the microprocessor that is looking at the effect that is having with the depth sensor. So the depth sensor will be working with that. It knows it's pushed all the water out, so it's expecting to see a rise. If that doesn't happen, then it will implement emergency procedures. So that's one end of the tank where water is allowed to go out, air pressure is allowed to come in. But when we're on the surface and we want to sink, what we have to do is open this up, allow water to come in, and at the other end, open that one, which allows air to get pushed out so water can replace it, and then they seal. But I'll just show you those working because they're very cool as well. Also, I had to redesign them, and I'll explain why I had to do that. That was a bit annoying, but that was the reality of building stuff. So at the moment, I've changed to plastic pipe feeding in. So here is the 2000 psi rated. This is I think this is 200. But I've changed those to plastic because originally I had aluminium pipes in place there. But if the angle was slightly wrong, tightening them up, they had to be absolutely perfect. If you got them wrong, then you were stressing the O-rings because they were slightly twisted in the chamber, in the tube. So by changing them to plastic, they organise themselves. So you get an even distribution of pressure on the O-rings. So it gives you that flexibility, really. So that's those. This is how these work. Pretty cool. And so we'll get them via a nano to all operate, doing things, programmed to do things at the right time, working in conjunction with the air pressure coming in and looking at depth pressure sensor rising or not. They all have leak detection in them, which is also wired back to the main detection center. And so if any water anywhere gets into any of these chambers, it automatically triggers the emergency drop weight, and it then becomes buoyant off its own. Yeah, that's pretty much where I'm at the moment.